and continuity of a complex function. A complex function w equal to f of z is tends to a limit L as z approaches a point z naught. For every real epsilon, there exists a positive real delta such that modulus of f of z minus L less than epsilon for a modulus of z minus z naught less than delta. Classical definition of a limit of a complex function. That is, for every z not equal to z naught in the delta disk of the z plane, f of z has a value lying in the epsilon disk of the w plane. In symbols, we write limit z tends to z naught f of z is equal to L. And here this is the figure representing the mapping of a complex. Here in this z plane, z is a complex number, and then in the w plane, f of z representing a complex number, and we denote it by w. So w equal to f of z. That means f of z means the mapping the complex number z to f of z. Okay, and here for every z not equal to z naught in the delta disk of the z plane, in this z plane, in this delta disk, is if every z not equal to z naught and if mod z minus z naught is less than delta, f of z has a value L lying in between this epsilon disk. That is, modulus of f of z minus L is less than epsilon. So that means therefore as z approaches to z naught, f of z approaches to the limit L, and we denote it by limit z tends to z naught f of z is equal to L. In real number system, we have a limit extending to x naught f of x is equal to L, and there x approaches to x naught either from the right or from the left, and we denote it by left hand limit and right hand limit. If both the left hand limit and right hand limit are exist and both are unique, then only the limit of the function exists. But here the complex number z is in the two-dimensional plane, so z approaches to z naught in different ways, that is using a straight line or a curved form. So there are infinite number of possible ways for z approaches to z naught. So for finding the limit of the complex function, we find the limit along all these possible paths, and if all these possible paths, the limits are unique, then only the limit of the complex function exists. In real variables, x approaches to x naught implies that x approaches to x naught along the number line either from left or from right. In complex variable, z approaches to z naught implies that z approaches to z naught along any path, straight or curved. Points representing z and z naught in a complex plane can be joined by an infinite number of curves. Now we have the continuity of a complex function. A complex function w equal to f of z is said to be continuous at z equal to z naught if limit z tends to z naught f of z is equal to f of z naught. That is, limit z tends to z naught f of z exists and is same as f of z naught, then only the complex function is continuous at z is equal to z naught. A function f of z is said to be continuous in a domain of the z plane if it is point of this domain. Now we discuss some problems in the continuity of a complex function. Show that the function f of z is equal to imaginary of z by mod z for z not equal to 0 and 0 for z is equal to 0 is not continuous. We take limit z tends to 0, imaginary of z by mod z is equal to limit z tends to 0 means both extending to 0 and y tending to 0. Imaginary of z is equal to x plus iy. So imaginary of z is, imaginary part of z is y, by mod z is root of x square plus y square. And here we consider the path y equal to mx, which is straight line y equal to mx. Then limit x tending to 0, y tending to 0, y by root of x square plus y square is equal to limit x tending to 0, we are replacing y with the mx. So we are replacing y with mx, the limit has only limit x tending to 0. So we are replacing y with mx, y equal to mx, and here denominator it is root of x square plus y square is m square x square, and we take x outside, then it is root of 1 plus m square. So its value is m by root of 1 plus m square, and which depends on m. So that means if m is different, that is if m is equal to 1, y equal to x, there is just one limit, and if m equal to 2, y equal to 2x, then we have another limit. Limit is not unique and it is depending on the value of m, hence the limit. Now we have another question. Show that a function f of z is equal to imaginary of mod z square by z 0 and 0 for z equal to 0 is continuous at z equal to 0. So here we have to prove that this function is continuous at z is equal to, take the polar form of the complex term. Polar form is z equal to r e raised to I theta, where r is the radius and theta varies from 0 to 2 pi. So if z equal to r e raised to I theta, we have mod z is equal to r. That is mod z square is equal to r square. So mod z square by z is r square by r e raised to I theta. It is r e raised to minus I theta. And that equal to r into e raised to minus I theta is cos theta, e raised to minus I theta is cos theta minus I sin theta. E raised to minus I theta is cos theta minus I sin theta. So its real part is r cos theta and its imaginary part is minus r sin theta. So limit z tends to 0, imaginary of mod z square by z is equal to limit z tends to 0 becomes r tending to 0. Its imaginary part is minus r sin theta and its value is equal to 0. So limit z tends to 0, f of z is same as f of 0 and f of 0 is 0. From the question we have f of z equal to 0 at z equal to 0. So f of 0 is equal to 0. Therefore the function f of z is continuous at z equal to 0. Now derivative of a complex function. Let w equal to f of z be a complex function of the variable z equal to x plus iy. Derivative of f of z to be defined by f dash z is equal to limit delta z tends to 0, f of z plus delta z minus f of z by delta z, provided limit exists as the same value for all the different ways in which delta z approaches 0. Delta z approaches to 0 in any possible path, the limit delta z tends to 0, f of z plus delta z minus f of z by delta z exists, then the limit is called the derivative of the function f of z.